My name is Raphaël Collet. I'm one of the developers and maintainers of the ORM, the Odoo server-side framework. And today we're gonna do a journey inside the implementation of this ORM. So, the implementation of Odoo's ORM is constrained by some requirements, of course. It has to be, you expect it to be correct, you expect it to be relatively secure, both in terms of respecting the access rights of the users that want to perform an operation, but also secure, technically speaking, against, for instance, external attacks and SQL injections, for instance. The data structures and all the code of the ORM is also heavily influenced by efficiency requirements. We expect, of course, the ORM to be as efficient as possible, and that is, we have to use data structures and algorithms that scale well for large data, and we expect also to use as few SQL queries as possible to perform an operation. That's because the cost in terms of time of every SQL query is huge compared to the cost of just simple computations in your Python code. The implementation of the ORM is, as many systems, shaped around a few key data structures. In this presentation, I'm going to focus on those data structures, and everything else, in fact, is simply defined in terms of those data structures. So all the core operations of the ORM can be easily described, and you can infer mostly what's needed to perform them in terms of those data structures. So I'm going to focus on the role of each data structure and also on how it's implemented and why it's implemented in a certain way. And I've chosen 5 data structures that we're going to look at a bit more closely. I'm not going to detail every aspect of the API or nitty implementation details like that. I want to focus on the essentials. And those are the core things that make the ORM efficient as it is now. The first data structure I'm going to focus on is the so-called registry. The registry is a place where every model name is associated to a Python class. This Python class corresponds to how you've defined your model in Python. And this Python class, it's also the class of the records returned by the method browse. So the records are actually an instance of that class in the registry. The registry also holds some other metadata that are specific to the database you're connected onto. Some of them are, most of them actually are purely technical things that we chose to put on the registry just for the sake of having them on hand. I'll show you now how the way you define a model will actually shape the class, the corresponding class in the registry. On your left-hand side, you see a certain number of classes, suggested classes, and this is the way you'd write them in your own code. So here, for instance, we have 3 classes, foo0, foo1, foo2, and you can think of them in different modules, for instance. Foo0 is the initial model definition, and the other ones are extensions of overriding of methods, for instance, or extension with more fields, more constraints, and so on. And in order to make a class that's kind of consistent with these definitions, on the right-hand side, you have what I call the model class, or the registry class, that is the class that's associated to the model in the registry. And that class is actually the class of all the records of this model. And you can see, look at the class. The name of the class is irrelevant, it's not important. The point is it corresponds to the model foo here, I call the model foo. And the base classes are crucial. If you look at in which order, for instance, an attribute lookup or a method lookup will occur, we will first look up foo2, that is the last class that defines the model, then foo1, the before last, and up to foo0, which is the one that defined the model first. So this corresponds to the reverse order of the model extensions somehow. So you first look up the last extension and then you go up to the initial definition of the domain, the model, sorry. And then you have an extra base class, which I'm going to talk in the next slide. The important thing here is that all the classes that the developer writes will actually end up as parent classes of the model, of the class of the records you're going to manipulate in your code. This is a slightly more tricky model. In here I show you a basic model, foo0, that inherits from a mixin class or another model actually. So the abstract model called bar here, you can think to, for instance, the mail threads. They're such a mixin model. And here in the class foo1, you say that the model foo will inherit from bar and from foo. Inheriting from bar and from foo means that we want the model class of foo to inherit from the model class of bar, and not just the class bar0, and then from the other classes that were defining the model foo. So if you look at the parent classes of foo on the right hand side, you see foo1, which is the last extension of this model. Then you have the model class of bar, which currently only has bar0 and the base class as an ancestor. And then you see the class that provides the first definition of the model. The advantage, of course, if you look at the method resolution order of these things, you will go through foo1, then you will look up the model bar, and then you'll continue through foo0 and then the base class. The base class there, it's actually a special model. It's a model called base, simply. And there's just a little trick in the definition of the models that all model classes actually inherit from that model class, except the base itself, of course. This allows, you see that base is the last in line in the ancestors order. It means that you can actually override a method that will actually be in the resolution order, will be placed after all the definitions of the model itself, or all the overridings of the model itself. We can make a kind of an overriding of the ORM itself, right on top of the ORM. Once you have defined such a class, because the model class inherit from all the class definition, the model definitions of the model, you can, by introspection, by analyzing the content of the class, you can retrieve the fields, some methods, and a bunch of tricks like that. And the registry, once it has built the classes, will actually set up, and mostly the field setup is one of the most important things in the ORM. Essentially for managing all kind of things like computations, dependencies, and dependencies between fields that are necessary, for instance, that have an impact on the record cache. So this setup, essentially, you introspect to determine which are the fields defined by the model. You will consider also the custom fields added to that model, and then the fields inherited from other models, inherited in the meaning of underscore inherits, and those ones are defined mostly as related fields to the parent model. And then there's a setup for each field to determine its own parameters, its dependencies, and so on. I'll come back later, especially on the dependencies, because the setup that determines the dependencies will actually build so-called field triggers. And that's the essential you have to know about the registry. It's about getting those model classes correctly, and of course there's a challenge of performance to make this setup as fast as possible. This setup is actually quite fast, unless except during an installation of modules or module upgrades and stuff like that, where it's a bit more costly. But when you're loading simply a registry to connect to an existing database, this whole setup is done once, and therefore is relatively fast. The second data structure we're going to look today is the cache of records, the so-called, the famous record cache. What's this thing? Well, that's a cache. It's essentially a database cache, but an augmented database cache, which means we store a bit more than what's in the database, because we also store stuff that are actually field values, but are not stored explicitly in the database. And this thing is specific to a transaction. That's why it's actually attached to the environment of the records. To see here I'm going to show you the prefetching of this cache. This is kind of a semi-magical thing in the ORM that makes things efficient, and many people don't really understand why. I'm going to here sketch you how this thing works, and you'll see from this description that we have some constraints on how the cache must be organized to be efficient. So the prefetching of the cache, what does that mean? Imagine you have the code here on my right hand side. Essentially you browse a bunch of records, and then you loop through each of those records, and for each you access the name of the record, the field called name. You don't want, if you have n records in the set, you don't want to make n queries. That would be really inefficient, really too inefficient, because if you have, imagine two nested loops like that, this would be just a nightmare in terms of performance. So what the prefetching does is to turn this n accesses to fields into actually a single query to the database. How does the magic work? Well, the first time you run the loop, you access the field name, and the field accessor will simply look up the cache for the given record. It will find that there's no value there. Therefore, it decides to fetch the field on the record, but not just the record itself. You'd like, in fact, to fetch on all the records in the set you're looping on. And there's a special attribute on the records, which is called this prefetch IDs. It's just an implementation detail, of course, but the important thing is that these prefetch IDs, they tell you other record IDs that are worth considering in the same set. So when you're looping, when you perform a loop on a record set like we have here, in fact, each record will know the parent record somehow, or the set, the big record set they're part of. And therefore, every record knows the other record IDs. And this information is passed from record to record, and here from the records variable to the record variable at each iteration. So we know all the records ID. What do? We look up all those records in the cache. We see they're not there, so we will fetch them all. And there's an extra bit of, for gaining performance. If the field itself is stored as a column in the database, you'll fetch almost all columns from the table of the model, because it's more efficient to perform it that way. And then, of course, once you've determined all the fields you're going to fetch, you invoke the method read, the low-level method read, to actually make an SQL query to retrieve that data and put it in cache. And then, after that, you re-look up the cache for the record and you find the value. If you don't find the value, it means probably an error happened, or you've got an access error. You cannot access this, field on this record, something like that. This was for the first time you go through the loop body. The second time, you'll look up the cache of the second record in the set, and this time, the prefetching that occurred the last iteration has filled in the cache, and therefore the cache is full. You got a cache hit, you got the value right away. And therefore, every subsequent iteration finds the value it needs in the cache. This is how the record cache prefetching works. If you look at where we look up the cache, you see that sometimes we look up the cache on one record, sometimes we look up the cache on a certain number of records. And then, for the read operation, we'll actually update the cache on a bunch of records. And therefore, we need a data structure that is as efficient as possible in those cases. Here, we have essentially what the record cache looks like. It's a dictionary containing nested dictionaries. The key of the first dictionary, the topmost dictionary, is the field. The field here, you can imagine the name of the model and the name of the field itself. So it's a field of a given model. And the second key is the record ID. It has the advantage if you want to look up n records, well, the field is the same for all of them. Therefore, you make one lookup for the field and then n lookups for each record ID. The same if you want to perform update, and the same if you want to invalidate the records. And in fact, if you want to invalidate all records for that field, it's just one operation. You just drop the value corresponding to the field from the dictionary. And this is why the record cache is organized that way. It's not organized per model, per record, but rather by field, because it's more efficient to do like that. We have a special case for some fields. It depends on the field then. It's the implementation is this way for the fields that are as such in database. But some fields are not exactly like that in the database. For instance, the translated field, they don't just have one value. They have, in fact, one value per language. It's also similar for company-dependent fields. The same field will have a different value if you look up in the context, if you look it up in the context of a different company. In those cases, those are the so-called context-dependent field. There is an extra key in the structure of the dictionaries. And essentially, this just adds one lookup to each operation you perform in the cache. Just one lookup, whatever the number of records. This is the structure of the record cache. The challenge here is that this cache must be consistent with the database. So the consistency of the cache is crucial for its correctness. So when things change in the database, you have to either just wipe away the cache. So if the cache is empty, it's always consistent. Or you have to update the values in the cache so that, of course, the values reflect what's in the database. In the past, we used it to invalidate quite aggressively the cache. In Odoo 13, we did a kind of a huge refactoring of the ORM, and we try to avoid invalidating as much as possible and instead to keep the data up to date. And this allows actually to save some queries when you perform operation, and this of course provides better performance. The next data structure we're going to look at is the to write thing, fields to write. What's the goal of this data structure? Is to essentially imagine you have a model with 10 computed fields. Each of those fields is computed by its own method and must be stored to the database. Every time you create such a record, you'll have to create the record, then compute each of the fields, and then for each field, you'll have to update the corresponding column in the table. We would like to group these updates automatically. Essentially, the goal of ToWrite is to minimize the number of update queries you perform on the database. And the idea is to group updates by record. This is the simplest way to minimize the number of updates. It might not be a global minimum, but it's already a reasonable minimum. So this data structure contains the column values. It's only for column fields, so stored fields and stored as column in the table. And this thing, of course, as it depends on the current transaction, it's attached to the current environment. The simplest way, this structure is relatively simple, so it's grouped by model. That's why you have model name as first key in this nested dictionary structure. It's first indexed by model name, then by record ID, and then for each record you have each field name associated to its new value. So the idea is that the operation write will actually not perform the update itself, but instead will fill in that data structure with the values that have to be written to the database. And there's another operation that takes that data structure, put all the information together, and will actually group everything first by record, so that you can say if you have updates, you'll have at most one update per record. And moreover, if two records have exactly the same update, so we update the same fields to the same values, then those records are automatically grouped. So if you compute, for instance, you recompute one field for a bunch of records, and all those fields have the same value, you'll perform one update. Which is, I mean, you cannot do less than this. The challenge, of course, of this data structure is to keep not the cache consistent to the database, but actually to keep the database consistent with the cache. This data structure is a way to prepare updates that are supposed to have been done on the database. So you're sort of collecting updates, not doing them right away, but do it as if they were done immediately. So the operation flush makes sure that all the updates you've kept are actually pushed to the done to the database. It keeps the database consistent with your changes. The method flush is automatically called by the methods like search, read, regroup, essentially all the methods that perform select statements on the database. And of course, if you're going to select something that's supposed to be updated, you'll first push the updates to the database before doing the query. In case you make manual queries inside your code, never forget to flush the data into the database. And flush takes optional parameters. If you call flush without parameters, you're flushing all updates, whatever the model. If you don't, if you call it with field names, then the system will first look up whether the fields are subject to some updates, and if so, it will flush the corresponding records. Next slide. We're going to show the fields to compute. Fields to compute, this is the next data structure. This one appeared in version 8, actually. And the goal of the data structure is to keep track of which records have to be computed, but have not been computed yet. And we use that data structure for stored fields only. Only stored fields are put in that data structure. Non-stored fields are different. And this thing is accessible on the environment. So the goal here, since Odoo 13, when we have fields to be recomputed, we try to delay the computation as much as possible. This has the advantage, if you touch several dependencies of a field, you will recompute it once, and not every time you touch a dependency, for instance. And the other bit is that once you delay those computations, you can actually collect then all the updates at once and perform them in the flush. Here, I show you, this is a simplified version of a field accessor. So the field accessor is the method on the field that performs like record.name or something like that. And I've highlighted some code there. The code that is highlighted is the one that can be reached for stored fields only. So stored fields will go through that code. First, you check whether the record has been marked to compute. If so, you compute it right away. Making this if before accessing the cache is essential, because it means that you can keep the old value of the field in cache, but still knowing that you have to compute that field. Advantage of that is that you can, for instance, increment a computed field, that is, reading its old value and putting a new value instead. Or you can just recompute it and realize that the new value is the same than the old value. In that case, you'll save an update. So, if you have a stored field, the first thing to do is to check whether it's been marked to compute. If so, you compute it and you use the toCompute to determine on which records you want to compute. So all the fields marked to compute are recomputed in one shot. Then you look up the cache, and in case you have a cache miss, as it's a stored field, if you have nothing in cache, it means you have to pre-fetch that field. And this is what the fetch method will do here. And what you do, you first look up the cache, you look at the fields, the records, to prefetch, determine the ones that don't have a value in cache, and you call the fetch method on them. And then once you're done, you access the cache again, and you should have what you look for in that cache. Here is the same. So if you compare here and here, this is the case for non-stored computed fields. If a field is not stored, it will never appear in the toCompute data structure. So toCompute, it's only for stored computed fields. Here, a computed field that's not stored will never fall into that. Therefore, the condition of the if is always false, and you first look up the cache. The way we mark a non-stored field to compute is by invalidating it from the cache. So that you have a cache miss there, and then you see, once you have the cache miss, you check if the field is not stored and must be computed. We call the compute method on the prefetch set of that record. And then we access the cache to get the value. So the fields to compute, this one is central for managing the fields, the stored computed fields, and knowing when to compute them and what must be computed. So of course it has an impact on the flush, because flush must first process the fields to compute. The computation will assign values to those fields, and the assignment will put this information in the toWrite data structure. And then the toWrite data structure is used to generate database updates. This is how we make updates to records on which you have computed fields, generate a minimal number of updates on the database. The challenge, of course, is managing the cache correctly, and especially the field accessors and the fields setters. The last data structure we're going to talk about, those are the field triggers. The field triggers have, the goal of the field triggers is to know what must be computed when you have made some modification. So assume you update a field's dependency, which fields must be recomputed. And so it helps knowing, determining efficiently, depending on the modification that has just been done, we determine what must be marked to compute or invalidated from the cache, depending on whether it's stored or not. And of course, this data structure is based on field dependencies. It allows to inverse those field dependencies. I'll show you an example. The example is something like a sales order. So you have here, I've suggested two classes, one with a sales order with a total, and the total will depend on a field on the sales order, which I call the discount. Like if you've got a global discount on all your sales order, and on the subtotal of every line in the sales order. And on the line, the subtotal is itself a computed field that depends on, of course, the price and the quantity of the product on the line. The field triggers is actually a tree data structure. It's a tree. The nodes in the tree contain a set of fields to mark, to be computed or to invalidate from the cache. And the edges of the tree are labeled by fields. In this case, for instance, you can see if you touch the field discount, so you have that, this is the topmost tree on the right-hand side. This is the tree which consists of a single node of the fields discount and line IDs. When you touch one of those fields, you have to mark total to be computed on the records that have been modified. Now look at the right-hand side, the tree on the left, below left. If you touched the field subtotal on a line, if you touch the field subtotal on the line, you will have to not invalidate anything on the line itself, but you'll have to inverse the field line IDs. Line IDs is a field on sales order. So you will determine which sales order are connected to this line I just modified, and on those sales orders invalidate or mark total to be recomputed. And that's the case also for the field order ID. The field order ID, of course, has an impact because modifying the order ID means the order ID is actually the implementation of line IDs. It's the inverse of field line IDs. So if you change the order ID of a line, it means you're somehow setting it to a different sales order. In that case, in fact, both sales order will have to be recomputed. The last tree here is if you touch at the price, for instance, on the line. If you touch the price, the subtotal of the line has to be computed. And then you inverse the line IDs. And for inversing the line IDs, you can actually just follow the field order ID. It gives you the sales order that has to be recomputed for total. So those are, in a very simple example, the so-called field triggers that are used to determine what to invalidate. And the invalidation, it works, it looks like this. I've, of course, again, simplified the code, but you get the idea with this. So this code, you have the method modified, and the method modified is called every time we touch a field on a record set. The record set itself, and fnames is a list of field names or a collection of field names that have been modified. So what you do, you're getting the field triggers of every one of these fields. That is, you're getting a certain number of trees, and you merge all those trees. And then you call the method modified triggers with that tree. And this method will actually traverse the tree until the record set you're working on is empty or there's nothing left in the tree. And this is recursive. So you first process the root of the tree, and what you do, those are fields to be computed. So you either mark them to be recomputed if they're stored, or you invalidate it from the cache, and therefore accessing those fields will automatically recompute them. And then you process every one of the subtree. So for every one of the subtree, you first take the field that labels the subtree, you inverse that field on self. So if the field, for instance, is a many-to-one field, you can just search on the fields model to say which records have this value, this record ID for that field. Or you may have the information in cache. If the field is a one-to-many field, like in the case of line IDs, the inverse field is called order ID. It's a many-to-one. So you only need to actually follow the many-to-one field on the modified records, and you know which records have to be marked to be computed and to process for the rest of the tree. That's why it's called for the recursive call. So the challenge, of course, here is to build these trees of plenty of triggers. The triggers, essentially, they reflect the transitive closure or field dependencies. So you take all the dependencies of the field and the dependencies of those dependencies until you've reached everything. Okay? So you recursively traverse the field dependencies, and essentially you traverse the dependencies one way and build a trigger tree the other way around. So the building of the tree is a bit tricky, but essentially make a transitive closure with field dependencies and build a tree following them. And then you put all those trees in a common data structure that's actually stored next to the registry. There are two challenges with the field triggers: is building those data structures efficiently, and they are really at the core of triggering recomputations. And part of triggering these recomputations is, of course, when you're inversing dependencies, you have to figure out, okay, if I've modified those records, which other records depend directly on them and must be recomputed for some field. So inversing those relations is the costly part of triggering the recomputation. And in Odoo 13, the major refactoring we've done with that is to try to use the information that's available in cache, especially for one-to-many, many-to-one fields that are inverse of each other, or possibly many-to-many fields that are also inverse of each other. If you have an inverse field at hand, use the information that you may have already in the cache. And this finishes my presentation. So those are 5 key data structures that drive the implementation of the ORM. Thank you very much. Okay, hello. So we're going to answer the questions that were asked in the chat. You can keep asking questions in the chat, and Xavier will be my kind of interviewer here.
Yeah, so I'll be asking the questions you were putting in the chat. Mm-hmm. And so the first question from Sunny is, what order are the extensions loaded in and used? So the modules get loaded, but what order do they get loaded in the registry? What is it based on? Is it based on the dependencies? Is it based on sequences? Is it based on just random stuff?
So you got 2 things here. So the modules are loaded in a certain order. So when you connect to an existing database and you instantiate a registry for that database, you will load all the modules that were installed for that database. And the loading order is fixed. It depends on the module dependencies. So if module B depends on module A, it will be loaded after module A. And then there's just a mechanism when there's an ambiguity, we use alphabetical order or something like that. But essentially, the order of loading modules is fixed. And then each module, the code of each module is imported. The classes that you've written, they will automatically subscribe themselves to say, I'm a class in this module. And for building the registry, what we do is each time we've loaded a module, we go and pick the classes that somehow that have been defined, in fact, in the code. We pick them in order and we process them we kind of inject them in the registry, either by instantiating a new class for a module that wasn't defined before, or by changing an existing model class and to insert the new class at the right spot, at the right place in the inheritance order.
Okay, and a follow-up question from François Lange. When you have two models in the same file, then how is the loading order between those modules defined? Or is it defined?
You mean models?
Two models in the main file, in the main Python file. In
the same Python file. So in fact the classes will be added in the registry in the order in which they're actually written in the file. So if you have a class for a module A and then a class for a module B, you'll first put the one for the model A in the registry and then the one for the model B in the registry. But actually the order in which you put these classes in the registry is not relevant. It's only relevant if you have two classes for the same model. Like you're defining a model and then you're defining another class, but that extends the first model. Then you know the order is first the model definition, in fact, and then the extension. It's kind of consistent with the order in which you've written your code.
A question from Phil DL. How can you avoid prefetching all the fields and just fetch specific fields you wanted?
There's two ways to tell that. I'm gonna switch to my, wait, here, I'm here, I'm there, where's my, whoop, 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 whoop. My computer seems to be lagging. Nothing happens. Okay, I wanted to switch to my computer. So you can prevent. So prefetching has essentially it's a double mechanism. First, you start off with one record on which you want to read one field. What you'll do is first find other records, typically in the same prefetch set, that are candidates also for this field, that actually are highly susceptible of being read, that field as well. So you'll find a bunch of records, and then once you find a bunch of records, depending a bit on the kind of the field, you will also select other fields to actually fetch together with the first field. And the rule is roughly, if you read a field that's actually a column in the models table, you'll typically read the other columns from the same table. There are a few exceptions like translated fields, binary fields. They're not written, they're not prefetched by default. But the other fields are. So you can prevent prefetching several fields by putting a special key in the context. And the key is called prefetch_fields. And if you set it to false in the context of your record, then you will essentially fetch one field at a time. But you will, of course, prefetch several records at a time. So that being said, so you can switch from prefetching all the fields to prefetching one field at a time. Oops, sorry. But you cannot specify which kind of group of fields you want to prefetch. It's something you cannot do.
Isn't it possible to use read just to avoid the prefetching?
Yeah, the one possibility, sometimes it's a trick we sometimes use when we have, in fact, kind of prefetching performance issues, like either we don't prefetch enough with having the prefetch fields to false, and at the same time we prefetch too much if we let prefetching all the fields. What we sometimes do is, before the actual code using the fields, we perform a read operation on the records that are supposed to be fetched, and you read the fields you're interested in. The advantage of that approach is that you will only somehow fetch the fields that are necessary, knowing that the method read will actually make sure the stuff is in cache, will actually fill in the cache with what it reads from the database, and then return all the values formatted the right way, the way you expect from read.
Okay, thanks. I hope this is clear.
So read has this side effect of filling in the cache with what you ask.
Just what you ask for.
Exactly.
And no more. So I hope that helped. And then a question from Joseph. Could you explain the difference between depends and onChange? Because they look very similar.
They look indeed very similar. The first thing is that onChange is a totally generic mechanism. It tells whenever you touch another field, a given field on a model, you run some code, and it's actually only used when you're filling in a form. So the onChange is when filling in a form, and you can only be triggered on one field of the current model. Depends is a kind of a similar mechanism when you're filling the form, except that you can depend on fields from other models. So you may have a dependency like, I don't know, line IDs dot partner ID dot whatever. You will actually depend on several fields and on fields on other models. And if those other records happen to be on the form view, the compute method will be triggered to recompute the field given all the changes. The trick is that the onChange only works when you're filling in a form, while the depends, in fact, they trigger the computation not only in the form, but also in the regular ORM operations. That is, all create, write operations, and so on.
That segues into a question from Ivan. When fields need to be recomputed, when they're invalidated,
yep.
When are they recomputed? Are they recomputed in the same transaction they were invalidated in, or not necessarily?
It depends on the field. In fact, for stored fields, so if those fields are in the database, in fact, they're marked somewhere to be recomputed on this record or on those records. And before closing the transaction, we actually process all those recomputations. It generates a certain number of updates. Then we flush all those updates to the database, and then only then we commit the transaction, we close the transaction. So the fields are never recomputed in another transaction. It's always within a given transaction, and the purpose, of course, is to make the transaction a consistent batch of changes. The non-stored fields, in fact, they don't necessarily need to be recomputed. Essentially, so if you have a computed field, it's not stored in the database. If you touch one of their dependencies, it's in fact invalidated from the cache, simply. If you don't access that field on the record, it will never be recomputed.
Okay, so
then it's recomputed on demand when you access that field. And that's also why there's two different mechanisms for knowing when to recompute a field. Depending on whether it's stored, it then uses this to compute data structure, or if it's not stored, then we use a simple cache miss, knowing that if the field is computed, we use the compute method to somehow fill in the cache.
Okay, and then different question from I1 and 1 mile code. How do the cache and row SQL queries interact? How do you safely perform SQL selects or inserts around ORM operations?
So you mean if you want to make an explicit query, SQL query in your code, how to make sure somehow that the ORM remains somehow consistent with
Right,
respect to what you've done.
Right, because sometimes you need raw SQL either because the ORM cannot express the operation or because it's a bit slow and you can go faster.
Essentially, so you have to synchronize two things. And remember, you have to use either invalidation of the cache and or, in fact, flushing. So before your query, typically you'll first have to think about flushing the fields that are necessary for the query to be correct. So you synchronize the database with your cache, in fact. So first flush, then perform your query, and if your query has changed some fields potentially in the cache, you have to invalidate those fields on the cache after having performed the query. So for select queries, you will only flush before, and the select itself does not change anything. But for update or insert queries or delete queries, of course, after those queries, you somehow have to, at minimum, invalidate the cache that may be impacted or that may be inconsistent with your changes, or possibly update the cache. But usually the simplest is to simply invalidate the cache.
Okay, well, sadly, we have run out of time, so the other questions we won't really be able to answer in video.
If you have more questions, I'll be available at some point in the community rooms.
Well, thank you for following this presentation and have a nice day.
Have a nice day.